I'm Kaylee, Mann. Can you hear me? Okay? Okay, everybody can hear okay? Okay, good. So, what I've been working on is a wireless platform that we mount on insects to stimulate them while they're flying. And with the goal of making flying micro-robots. So one question many people ask is why do we need flying micro-robots? So here's a group brainstorm we came up with for various things we can do with flying micro-robots. So there's the obvious military applications of reconnaissance and those sort of surveillance things. You can also use them for wireless sensor networks, stuff like that. There are also some funnier applications, such as tormenting your cat or delivering extremely small tacos. So people have been trying for a long time to make really small flying vehicles, and here's some examples of this. Some of them don't have internal power, and some of them still can't match the performance of flying insects. Why would it be useful to use insects as flying micro-robots? So the reasons we think insects are a good way to solve this problem is because they're already flying, they're already very good at flying, and they're more durable than many of the things we can create. They've already solved the problem of creating small flying vehicles. And they can fly for a long period of time. They have very good power to weight ratio. But there are some drawbacks. They're not as precisely controllable as a robot because they're not really a robot. And you do lose some ability to control them really fine. There has been prior work on how to control flying insects, to control their flight patterns. So much of the prior work has been neural and neuromuscular stimulation. So that's inserting electrodes into the insect, doing surgery, implanting electrodes, and then stimulating those electrodes with a microprocessor. So this is an example of that. Also, it has a radio, and you can see the antenna coming off of it. But one problem with this method, so this is basically the flight loop of a insect. It has its brain, it sends out commands to its muscles, which are the actuators. The real world does something, it flaps its wings and it moves. And then it senses how that affected its state, and then it runs through this control loop over and over again. So what we've been doing with this prior work, or what has been done with the prior work, is we introduce an additional sensors and an additional control system which stimulates the same actuators that the insect is stimulating with its brain. So this is what's been done in most of the prior work, but the problem with this is that you have two control signals that are fighting for control of the actuators. So the insect's brain is trying to tell the muscle to go one way, and your controller is telling the muscle to go the other direction. So we've devised a new method, and our new method is where we break this link between the real world and the sensors by, for example, painting over the insect's eyes. And as we always do, we introduce sensors so that our control system knows where the insect is. And we introduce our control, and instead of stimulating the actuators directly, we stimulate the sensors and are able to affect this feedback loop in the insect's mind to convince it that what it wants to do is turn in the direction that we want it to turn. So this is basically the motivation for our method of controlling insects. So the insect we're using is Schistocerca americana. It's an American locust or a grasshopper. They're actually the same insect if you didn't know that. And the one interesting thing about these insects is that they have, if you look at the insect, you only really notice the two big eyes, but they actually have 5 eyes And they have a very interesting visual system. One of the things they do in their visual system is they have what's called the dorsal light response. So the dorsal light response is basically the amount of light falling on the right half versus the left half of the insect's face. So what the insect presumably uses that to do is to detect what orientation it's in. So if the insect is turned one direction, it will see more light on one side of its face, and one eye will see more light. And then if it's turned the other direction, the other eye will see more light. So this is one of the core ways that an insect detects what orientation it is. So what we do is we put LEDs on top of the eyes in order to affect where it thinks it is, and thus affect where it goes. So we've done some tether tests of the insect. So these were some early tether tests where we have some LEDs over the eyes. We were also testing the center Ocellar-Based, which is right here. And what you can see here is when we blink the lights, its head actually twitches to the sides, which is an indication that it's actually trying to turn, because insects turn their head whenever they're actually trying to fly. And we also did it with a high-speed camera, which is why this is so grainy. But in this one, you can actually see that the abdomen is being deflected in one direction, and then goes back the other direction when we apply the opposite stimulus. So it's actually moving its abdomen in an attempt to turn. So these original tether tests were pretty promising, and we got good results. So the next step is moving on to a completely wireless system, and that's where I've been doing most of my work. What I'm trying to make is basically a versatile platform that we can put on these insects to do various types of things. Our particular interest is stimulating these eyes, but this system could, in theory, be used for many different types of stimulus, and could even be used for the traditional electrode stimulation. And one thing to note about this is that having a wireless platform on an insect that can stimulate the insect is a really good way to investigate more things about insects, insect electrophysiology, and how insects fly. So it's a good way to learn more about how insects actually work. So here's my device. It has a battery on the bottom, and then it has an IR receiver, just like the IR receiver you have in a remote control or on your TV. And it also has a little microcontroller and a tracking dot so that we can know exactly where the insect is. So we call this the backpack, and we mount it on the pronotum of the locust. And that pronotum is right behind the head, and it's a nice rigid place that you can just glue this to, and it stays really well. And we also have these micro springs that we use out of really fine wire coil so that we don't restrict the head movement where the LEDs are connected. So our system is 280 milligrams. And it runs for 4 to 5 minutes right now, although that can be extended for hours of sleep time. So if you're only stimulating occasionally, that's 4 to 5 minutes of continuous stimulation. Another advantage of this system is that it's very non-invasive. There's no surgery into the insect. There's no implanting of electrodes or anything like that. You just glue the backpack onto its back, and then glue the headpiece with the LEDs onto its head. So this is our overall system. We have our insect, and we have a Vicon system, and that's what is able to track the dot we put on the back of the insect in 3D, so we know exactly where the insect is all the time. We also have the infrared beacons so that we can communicate with the backpack that's mounted on the insect. We needed lots of different IR beacons around the room because it was a challenge to have the IR beacons and not have them interfere with the Vicon system, which also uses infrared. So we send commands from the computer to the IR beacons, and we can also read the insect's exact position via the Vicon system. So we can do there's a lot of possibility for control in this because we have it all set up for a feedback controller, basically. So here's an example of some tests we've been doing. So there was a commanded right turn, basically. You can actually see the LEDs blinking on its head. And then we have a commanded left turn there. Then we have to always go catch the insect after it runs. I think this is another turn. So yeah, we were able to get sort of basic directions that we want the insect to go. So compared with the past work, our wireless system is really light, and part of that is due to using these very small IR modules. All of the previous work used RF, so it used radios to communicate. So that's one thing to note. And also some of the systems used did run for longer. So there's some trade-off we're making here. But what we really were going for was a very light system so that we could use it on these small insects such as locusts. Because really anything above our weight of 280 milligrams is really too much for a locust to reasonably carry while being maneuverable. And this also means that we can use it on lots of other insects. For example, dragonflies are really good flyers and they fly really fast. So dragonflies are another insect that we want to be able to test this on. So. It also has a really low part count. There aren't very many parts on this, so it's a pretty simple device that anyone can theoretically assemble. So you just have basically a battery, an IR module, the microcontroller, basically the computer on the backpack, and the LEDs that are actually stimulating the eyes. And all of these parts are parts that you can just get online. They're just commercial off-the-shelf parts that you can get from somewhere like DigiKey. One challenge was extending the battery life so that we had a reasonable flight time. So there were different power modes that we used. So basically, when we have stimulation enabled, it can run for 3 minutes, and then if you disable stimulation for some of that time, you reach to 4.3 minutes. But you're not stimulating all the time, and so when you're not stimulating, you can put it into sleep mode, and that can extend the battery life for a really long time. And that's sort of the idea behind this, is that you aren't actually stimulating the insect all the time, because you really just want the insect to go in a general direction. So you really only turn on the stimulus to correct it when it's going away from your direction. So what I'm currently working on are new modes of stimulus so that we can actually stimulate in different ways. So we can add the capability of stimulating with electrodes. We also want to make a feedback control loop so that we can more precisely control these insects. And also, we really want to run more experiments with these insects and build more and more insects, so we basically have a swarm of controllable insects. I think that's it. I'd like to thank everybody in my lab, Professor Harvitz, the Surf Rose Hills fellowship and everybody who contributes to that, and my advisors here. Thank you.
Questions?
I noticed your test was able to create left to right movement, but what were you doing for ascending or descending flight?
So that's what we're investigating the center eye for, the median ocellus. But we haven't completely worked out how that works. And so right now we're trying to concentrate on turns, and that's something we're gonna have to figure out later. So we haven't completely figured that out.
Do you think that the IR control mechanism is going to be able to scale to like real world applications? Because it seems like in the room that you have line of sight to the receiver.
Right, so it wouldn't work for everything. It wouldn't work for like long distance communication. But it works pretty well, especially for indoors, if you want to do some sort of indoor aerial vehicle, which is for some of these applications it would be useful, or if you have line of sight with it. You can also make these IR beacons really big, so if you have a really big IR beacon, you can transmit these signals pretty far.
Is it possible to link, instead of having the IR beacon, you have a radio transmitter instead? That way you don't have that line of sight problem, or is there easy?
Right, so there is sort of a trade-off there. We could use a radio transmitter, and that's something we're looking into. But there is definitely that trade-off because commercial off-the-shelf radio transmitters always generally take external components or use lots of power. So that means that they're basically heavier and they have the potential of using more power. So the main concern was lightweight, and these IR modules were the smallest things we were really able to find commercially.
Well, thank you very much.